class now. I was doing something when suddenly a Dalek walks into my classroom.
So there's this hunter, and he wants to shoot a monkey for some reason.
Welcome to this week's physics lesson. This topic is on introducing the concept of speed. We can see the equation we're going to use here, and this is a little photo from part of the presentation later on. You can see a ball rolling down this chute. So speed is a commonly understood idea. It's something that's quite natural and most people have a fairly good picture in their head of what it means. In physics though, we want to be a little clearer than most people are, and we want to be quite careful with how we use those terms though. So as a proper definition, what we're going to say is that speed can be measured in many different ways, but it's always going to be some distance divided by some time. You could say that you're going to travel in so many meters per second, like this fighter jet here, or perhaps in kilometers per hour, or maybe in miles per hour if you're on the roads. In general, speed is how quickly your position changes, how much distance you're going to cover every unit of time. The reason we're starting to introduce calculations with this topic is hopefully it makes it a bit easier. For example, this table here shows various sums that are hopefully quite straightforward for most people. If we have a 50 miles being travelled in 1 hour, well, the speed is 50 miles per hour. If it's 40 miles and it takes 2 hours, well, obviously that means you're going to only go 20 miles for each hour. If we swap out our units and instead talk about kilometers, well, it's the same idea. 2 kilometers divided by 2 hours means you have 1 kilometer per hour. The idea is that whatever units we use here are the units that end up coming out the other end of our calculation. The standard units for science isn't the kilometer or the mile, it's actually the meter for distance and seconds for time. So most of the time in physics what we'll be doing is dividing a number of meters by a number of seconds. In this case 20 over 2 makes 10 meters per second and 200 over 5 makes 40 meters per second. Do note that the mph and the kph, which is common everyday abbreviation for miles per hour and kilometers per hour, is not transferable to meters per second. If you write MPS, we will sadly consider that to be incorrect. This is meters slash for divide by seconds. To give you a sense of how big a speed is, have a look at this table here. This is from Wikipedia and it lists some of the slowest things that we can measure all the way up to some of the fastest. You might not notice it, but the continents that we're standing on move by around 4 centimeters every year. So that's a distance divided by a time. It's a very small distance divided by a very big time. That means the thing's going very slowly. Snails are famous for their low speed. They only go about 1 millimeter per second, or 0.001 meters per second. If you're walking quite briskly, you can maybe almost do 2 meters a second. If you're cycling on the road, it's about 4. And a sort of really fast kick, which is about, almost 8. That's one of the faster parts of the human body. People that sprint can go up to about 12. Usain Bolt's world record attempt or world record score was approximately 10 seconds for the 100 meters. So that was his top speed, but his average speed was a little bit lower. We'll have a look at that later on. It turns out most road cyclists actually go at the same speed as a sprinter. So if you want to become an exceptionally good racer, well, you can spend your whole life training to run better, or you can just buy yourself a bike. Technology is quite nice that way. You might also notice here that if you compare the average speed of a cyclist to the speed limits on most roads, they're actually comparable. That's one of the reasons in built-up cities, cycling to work is actually sometimes more effective than driving. It also has other health benefits. If you're in a less built-up place, the speed limit tends to be a bit higher, and out on the main roads, it can be up to about 27 meters per second. That's the same as maybe 60 miles an hour, or almost 100 kilometers per hour. That is kind of close to hurricane speeds, and if you go a bit higher, you end up hitting into some pretty impressive speeds. So this is the fastest a human-powered machine has ever went, basically a big fancy bike, and if you ever go paintballing, you might notice the projectiles are pretty darn fast. This is the muzzle velocity, that's sort of how fast they get shot at. And if you're on a plane, well, you're traveling about 250 meters every second. That's 1 kilometer every 4 seconds, or roughly speaking, a mile every 6 seconds. Really quite fast. The fastest land speed we've been able to achieve with a big car was this number, and that's actually pretty close to the speed of sound. The speed of sound is close to this for a good reason. Turns out if you try and go faster than the speed of sound, you have to overcome a big pressure bubble, a big shock wave. So that's one of the reasons the land speed record hasn't gotten much higher. Fighter jets can go much faster than this though, but when they first burst through that sound barrier, it's really quite a big challenge. The Mach system is based on that. Mach 1 is the speed of sound for that reason. But anyway, back to more sort of relevant things for you directly in your physics class. The equation you'll know and love from maths is written here in words, but in physics we're far too lazy for that. We tend to prefer to use shortcuts to make everyone's life a fair bit easier. And this is, I promise you, a very, very useful shortcut. It makes everything better. There is just one downside, and the downside is when you happen to learn it for the first time, unfortunately, you've got to go through a process where you have to learn these new symbols, which can be an extra barrier and it can slow you down a little bit. But thankfully, distance is given a symbol d, so that kind of matches, and time is given a symbol t. That's quite straightforward. The one that's perhaps a bit strange is that the symbol for speed is not s. You might have been told in maths that is the symbol that they use and they can do whatever they like, but scientifically speaking, the internationally recognized symbol for speed is actually the v. And it's to do with the proper word for speed, which is velocity, but we'll come back to that in fourth year. So v is the correct thing to use here, and I'd really appreciate it when you do your homework if you could stick to that, please. There's also this little bar on top, so this term is pronounced v bar, and that indicates that we're not talking about a top speed or a low speed, we're talking about the average. If you imagine a runner, at the beginning they'll be going quite slow, then they get up to max pace, and then they might slow down a little towards the end. That's all very well and good, but we can't actually measure their speed at all those different times. All we can really work with is the overall average. And this little bar is just a nice physics way to emphasize that. So here's our first example, and I'm sure you're familiar with it, but let's go through it to see if we can learn a bit more about what's really going on when we do these type of measurements. Alice and Bob here are at sports day, and they're going to have a 100-meter race. Fun side note, we choose about 100 meters because that's quite a good distance for getting people up to their maximum speed. It takes maybe 20-30 meters to get to your peak speed, and most people can maintain their maximum speed for the rest of that journey. So it's quite a nice way of measuring it. And in this case, Alice and Bob are starting at the same place, ending at the same place, and both of them are therefore going to travel the same distance, but they do it in different times. Alice takes 20 seconds, which is quite a respectful number, and Bob, well, I guess he's Usain Bolt because he managed it in just 10. Well done, Bob. Most people recognize automatically that this smaller time means you must have went faster. When you do your 100-meter sprint, what we're interested in is seeing who can run the fastest, but we don't actually measure that. If you have a look at the PE department, for example, if they have a scoreboard somewhere, they're not going to tell you what your speed was. They'll tell you what your time is, because that's what they actually physically measure. And most people know the pattern that smaller time means you did better. And that's kind of what people remember. But it's important we don't get too carried away. For Alice, we have velocity or speed is equal to distance over time. Her distance was 100 meters, so we swap that in here. Her time was 20 seconds, so I'm going to take the t and replace it. And then I've got a sum for my calculator. 100 over 20 makes 5, and I look at the numbers I put in, 100 meters, 20 seconds, and that tells me the units that have to come out here. Because I wrote meters in and seconds in, I get meters per second out. The same sum works for Bob. I've done it in a different color just to help you follow it, but we always start with our equation. Speed is distance over time. That gets me a nice lovely mark straight away. I then put his distance in, which is the same as Alice's, and his time in, which was 10, and out pops the number from the calculator, 10, remember the units. All done. So in this case, we can see that Bob was travelling roughly twice as fast as Alice, which means it took him half the time to make the journey. Hopefully that makes sense. It turns out human intuition isn't quite perfect with these things though. So one interesting sort of side note is if you study people's understanding of speed and distance and time when they're very young, people aren't very good to begin with. See, in this case we have Charlie who's going to move with an unknown speed, and we're going to work that out. And it's going to take him 20 seconds to go along this journey. Bob is going to do exactly the same as he did before. He's going to travel 100 meters in 10 seconds. So that means he starts off halfway towards the finish line. He's kind of cheating. And if you were to ask people who is traveling the fastest here, not who's going to finish first, well, you might get funny results. You see, it turns out from the sums that, well, Charlie's got twice the time to do twice the distance, so it all works out that he's going to move at 10 meters per second, and Bob's going to do the same. But if you were to take the rule we said before and go too far with it and say smaller time means you're the best, you might end up with a wonky conclusion. You might say, well, Bob did it in less time, therefore he was going the fastest. But that pattern only works if you're talking about people going the same distance. Here you have to be a bit more careful. But anyway, back to the interesting side note. If you were to have a bunch of young primary kids standing at the stands on sports day and you were to ask them who was traveling fastest, one of the weird things is they will tell you that Bob is the fastest. And the reason for that is because he's just the one that's in front. Even if Charlie was running faster, and even if Charlie was going to win the entire race and was catching up with Bob, young children will always just tell you whoever's in front is the one going the fastest. They completely miss the fact that telling you where you are doesn't actually link to your speed. You can be in front and slowing down. Maybe Bob's been injured. You can be in the front and going the fastest, or you can be going at the same speed, like we are here. When people get a bit older, they start to pay attention to the gap. See, if you see that the gap between Charlie and Bob is starting to get smaller, that tells you that Charlie must be moving faster. But if you think about it, it might be quite strange. When we look at someone moving, we can't really tell you what their speed is. We have to use these little clues to help us figure it out. In this last example, I want to emphasize the average in average speed. Debbie here is going to do a 200-meter race, but she's going to do it in two parts. In the first part, she's doing really well. Just like Bob, she goes 100 meters in 10 seconds, and it works out her speed is 10 meters per second. Very good, world record. But after that, she gets a bit tired. And the next 100 meters she's got to run, well, she doesn't do nearly as well. She takes a bit longer. She takes 20 seconds for that. And we could work out for that part of the race what was her speed. And we end up with a value of 5 meters per second. But really, the question should be not so much what was her speed at the first bit and what was the speed at the second bit. That's not how people time things for the 200-meter sprint. Instead, what we would normally be working out is the overall average. So if you were to take these two numbers and try and figure out what the overall average would be, you might guess it's somewhere in the middle, and it is somewhere in the middle, but it's not halfway in the middle. And that's the bit that's a bit strange. If you're asked for the speed of an overall journey, all you ever do is to work out the total distance. Here that's 200 meters. And you take the total time. Here that's 10 plus 20 makes 30 seconds. And you do all the distance divided by all the time, and that gets you your sum. Technically, anytime you measure anything, that's what you're doing. You can't ever tell if someone was fastest at the start or the end or any of that sort of stuff. You just have an overall average. There are a couple of examples about how I would normally encourage people to measure these things in class. The point is that even if you understand the mathematics, it can actually be quite tricky. This is a marble loop-the-loop, and it goes around here, and people love the toy and they play with it, and that's great, and people seem to feel that it's quite easy to measure the speed, but it's actually quite tricky. You can measure the time with a stopwatch well enough, but again, it's harder than you think, and then the biggest issue is measuring that distance. There is a trick that's quite nice. What you can do is you can lay a piece of string all the way around the track. It takes a lot longer than you think because it tends to fall loose, but if you do that and then you take the string out, straighten it, and measure it with a meter stick, you'll find in this case it's about 1.39 meters. It takes about a second to go round, so average speed equals distance over time. 1.39 over 1, that's 1.39 meters per second. That would be how I'd show you this in class. A second example I often use is this little other marble toy here, where the ball's actually going back and forth as it falls slowly down. It takes a fair bit longer. This one's really challenging to actually physically measure, but it's quite a nice one all the same. One of the things that's quite common is people, once they've fed the string in, they get kind of fed up with that. It's quite frustrating to do, and then they take their measurement, they write down, oh, it's 80, and then away they go. But there's a deliberate mistake here. So if you say the distance was 80 centimeters and the time was 1.5 seconds, alright, fair enough. Speed is distance over time, 80 over 1.5, and you get 53 out. And then people remember the units for speed should be meters per second, they write that down, and then they move on. But there's a problem here, and you should be able to spot it. 53 meters every second is crazy fast. That's flying down the street like a car that's like going 100 miles an hour. Really, really fast. Probably wasn't what happened here with our marble. And the mistake is the units up here. You see, this was centimeters that went in, so it should have been centimeters that came out. The answer would be not 53 meters per second, but 53 centimeters per second. That would be fine. But that isn't the usual unit, so the better thing to do is actually to write your distances in meters at the start, and your time in seconds at the start. And that way, when you put them in, you don't have to worry about correcting units. I shot this footage at home so that I can show you one of the difficulties with measuring time associated with some motion. Here we have an 8-foot slide and it's about 2.44 meters, and we're going to roll this ball down it. When I click this timer, it'll start timing, and when I stop, when I click again, it'll stop. It's quite tricky though, because it's a very short time. So let's try and see what happens. Ready, steady, go. Stop. And we get 0.769 seconds. We'll try again. So ready, steady, go. Okay, that one didn't work out. One more time. Go and stop. And I get 0.769 again this time. So when I did this in practice, I actually got quite a few different numbers, and I'm not going to show you them all here because it'll take a bit too long, but it's quite tricky to judge exactly when it starts and exactly when it stops. So this is an example of some of the numbers I had when I practiced this, and now you've got a bit of a problem, because which number do you use? If you're taking time measurements and you're not sure if they're good enough, well, good scientists will take several measurements and they'll try and get a sense of what the best value is. But once you've got a whole bunch of them, you can't just pick and choose whatever you want. What you need to do is calculate an average. So that's what I've done here. And the average of anything is you add up all the individual values and then you divide by the number of measurements you've made. In this case, that turns out to be about 0.72 seconds. If I now take that and the distance and put them both into my equation for working out the speed, I find I have a value of 3.379501385 meters per second. Now, many people write down that number because they think their calculator is perfect, and if the calculator says something, it must be true. Who's going to argue with the calculator? Well, I'm going to argue with the calculator. You see, these numbers are pretty much made up nonsense. We cannot possibly claim to know this number that carefully, that precisely. We measured our distance to the nearest sort of millimeter. We measured our time quite roughly, actually. This one here is about 0.6. That's almost a whole, so that's almost double the value. That's how rough our values are. So our speed value is going to be pretty rough as well, because if you use rough data going in, you get rough answers coming out the other end. So claiming that all these numbers are known is just a bit misleading. And in physics, we round our numbers to show people how confident we are in them. So this would be considered incorrect, because we're kind of pretending we're perfect when we really weren't. So we need to round this value, and the usual rule is to round it to have the same numbers as the data, but here I'm actually going to round it a bit more. I'm going to round it to 1 decimal place, because I really don't trust this time data very well. So 3.37 rounds up to 3.4. My second example here is a little toy car being pushed across the kitchen floor. And the point I want to teach with this one is that sometimes you don't really have an effective way to measure the distance directly. Here, I did have a tape measure, but I've chosen not to use it. But there are sometimes a trick. If you have a unit that repeats, this could be the length of your shoe that you've paced out, it could be the length of a stride, it might be a big branch that you happen to have, it could be the length of any object you have. If you have multiple ones of them in a path, well, you don't have to measure the whole journey. See, here I have 5 tiles of distance, and from my video, that's all I'm taking, 5 tiles. Separate from that, I went and got out my tape measure and measured just 1 tile. This is quite handy if you were going to do this in a huge hall where it was really, really big. And it turns out each tile is just a little bit under 0.4 meters. What I can now do is work out the total distance by doing 5 tiles times this individual tile to get the total. I also separately timed the journey this car took with a stopwatch while watching the video. If you like, you can have a go yourself. But I think it turned out to be about 2.59 seconds for the time, and my distance, as I say, is 5 multiplied by this number here, and that gives me this top term. Again, if I put this into my calculator, I get a very large number of digits. Most of them are silly, so we round them, and I have a final answer of 0.77. Notice the bar still here. That's because in this case, the car started off going quite quickly, and then it slowed down due to friction, slowed down, and stopped. The previous example was the other way around. On the slide, the ball started off going quite slowly, but then it rolled faster and faster going down. In both cases, I've been talking about the average speed, so I don't have to try and deal with that complexity. This final slide shows you your homework. What I'd like you to do is carry it out on paper, just like I have been so far. Write down the equation, put in the numbers, do the sum, and then round it. I know it might seem silly to write out the equation for every sum you're doing it, but trust me, it's a very good thing to practice. It's an excellent habit to get into. The last part of this homework is designed to give you a chance to be a little bit creative, just like I was. It's not a free license to go and ruin your poor parents' sort of day. You can't rearrange your entire house or damage anything like that. Try and be sensible, but I'm hoping you'll be able to find something that will move at or near your house. If you find it quite tricky, probably the easiest thing for you to do would be to go out into your street and walk between one lamppost and another and count the number of steps. You can then sit in your kitchen window with a timer and time a random car passing by. That way you have the time for the car to go that distance, and you know the distance in number of steps. But hopefully there will be a bit of variety. Use your imagination, find something. I've given you a few other examples here, but hopefully this can give you something interesting to do. Because you all have different choices, I would like you to be very careful about communicating what that choice is. So directly state exactly what it is you were measuring and how you've measured it. That's all from me. I wish you the best of luck. Hopefully you have some fun.